Okay, so first of all, I would like to thank the organizers for giving me an opportunity to present my work. Today I'll give a talk on the topic, a model of thermophoresis of colloidal proteins in water. This work has been done in joint collaboration with Angad Singh, who's a BSMS student at IISc Pune, and Professor Arijit Bhattacharya. So this is the outline of my talk. I'll just give a quick recap to Brownian motion, and then we will dive straight into the problem of thermophoresis. So Albert Einstein in 1905 gave a theoretical description to understand Brownian motion, and what he derived was this diffusion equation, which tells you how the probability density evolves with time. So in his theory, the fluid was uniform or homogeneous, and that is why the diffusion was a constant. And uh, and uh, and and his work also gives us a microscopic origin to something called the Fickian diffusion current. Now, inspired by Einstein's work, Sidney Chapman in 1928 generalized Einstein's theory of Brownian motion to inhomogeneous fluids. And what he found out was when the space becomes inhomogeneous, uh, yes, so so when the space becomes so when the space becomes inhomogeneous, there is emergence of this additional current, which is proportional to this gradient of diffusivity, and that is called the non-Fickian current. And now your total diffusion currents look something like this. Now I will go straight into the problem of thermophoresis. So by thermophoresis, I mean a particle flow in a vertical direction in response to some externally applied field. The direction of transport is quantified by something called Sorry coefficient. So, okay, so if you look at this picture, I have a colloidal particle which is immersed in a fluid, and on one side of the fluid, suppose I attach a cold reservoir, and on the other end I attach a hot reservoir. So what would happen is that there would be emergence of a temperature gradient, and it is seen that some particles in response to this temperature gradient move in the colder direction. This is called positive thermophoresis, whereas few other particles, they move in towards the hotter reservoir. That is called negative thermophoresis. So in this talk, I'm going to focus on proteins, colloidal proteins, which are put in water. And these proteins are lysozyme, which is found in your egg white, BLGA, which is found in your milk, and polyl-lysine. And the reason for studying this is because a lot of experiments are available and done. Secondly, secondly, it is well known that electrostatic interactions don't play an important role, or they play a negligible role in this system. So your fundamental physics won't be masked by this electrostatic interaction, and plus you have this very non-trivial Sorry coefficient sign inversion. So what happens is, at some temperature lower than some critical temperature, the Sorry coefficient is negative, but above that critical temperature, the Sorry coefficient becomes positive. So in this work, we are going to look at this, and how are we going to model it? We are going to say that thermophoresis is the balance of three currents: the solvation current, the Fickian current, and this Chapman current, which has normally not been taken into account in the literature. Plus, the diffusion becomes inhomogeneous because of the presence of this explicit temperature gradient, and also because your protein is a structured object, so it can have some concentration dependent effect. So here I show you the experimental data, which is from this paper of Piazza, in which y-axis is the Sorry coefficient, x-axis is the temperature. You can see at temperature below this critical temperature, the Sorry coefficient is negative, but after that it becomes positive, and similarly for both the proteins of BLG and polyl-lysine. And what we have been able to show is that we have been able to come up with the model which agrees well with the experiment. And the theory of the model is like this. You write the total current, sum of the diffusion and solvation current. Now your total diffusion is composed of two parts. bare single particle diffusivity, and some collective effect, which is dependence of diffusivity on crowding. Now this bare particle diffusivity is given by the local Stokes-Einstein thermal energy by damping, and here you have this viscosity of water. This viscosity of water also has some small correction because of the presence of thermal gradient, and this correction is proportional to the thermal expansion of water. Plus this dependence of diffusivity in the model, we have taken it to be power law, where beta is some exponent of the concentration, B is some reference. And what we have also shown that the solvation terms takes a form something like this, T multiplied by the gradient of temperature, and A is a constant. So in this model, we have three fitting parameters, C, beta, and A. And with these three parameters, what you can do is that you can show that the Sorey coefficient takes a form something like this, where this term comes only because of consideration of this non-Fickian contribution, which is like this, and this A just gives you the shift, the solvation just gives you a shift, and the beta, which is the exponent of concentration, just tells you about the regime in which like you are looking. Okay. So here I compare these three current densities for the lysozyme, polyl-lysine, and BLGA. You can clearly see that solvation is always positive. This Fickian current is negative below the transition temperature and critical temperature, and then it becomes positive. And this non-Fickian current always is the strongest, and it always remains negative. So the conclusion is that non-Fickian current is very important, and it needs to be taken into account to understand phoretic phenomena like thermophoresis. These are the references. You can find more details of the work in this paper. And I would like to acknowledge CSIR and Angad and Arijit Bhattacharya for this work. Thank you.
Let's thank the speaker.